That's what we're going to be doing. So, hello everybody. Welcome to today's mini lecture on the benefits and fun that machine learning can provide. So I know Chad last weekend gave a short presentation about how to use sklearn for figuring out or correlating names with gender. Well, today we're going to go into a even more complicated example, which uses a regression and correlation in order to predict the survival of passengers on board the Titanic. So screen share. There we go. So can you guys see my screen okay?
Yes.
Yep.
Cool. Unfortunately, I cannot see the chat, which is a shame. But I can see when notifications pop up in there though. So if you guys have any questions, just, no need to raise hands, just turn your mic on and talk it out. So let's see here. So the first thing that we always wanted, also before I launch into the code, a thing that I'm using is called Google Collaboratory, which is one of the most amazing tools ever, in my opinion. So here, let me the main page. So basically, a collaboratory is like a Google Doc for Python. So what I've given you guys right now is a view only mode one. But if I made it editable, for example, then everybody could write their own code cells. You would have shared runtime. So like it's sort of like mixing VS Code with Google Docs for Python. And this is also very helpful because if you're running something, especially for machine learning that has like thousands or millions of data points, you can actually connect this to Google servers and use their GPUs as well in order to accelerate the runtime, which is really cool. And the best part is, as well, it is entirely free. So using Google Colab is great if you're trying to, like either write something like a full algorithm or even just, making a small piece of test code. It's a fantastic resource. I highly invite you guys to check it out. It also lets you nicely mark up your code. It's got some very cool, color shading and stuff. And also, if you want to say add in like a big block of text describing, like, for example, here, I'm trying to describe the data set. You can just add it in as text. You don't have to, add it right up in comments and put exclamation marks and hyphens and so on and so forth. It's actually like nice marked up text. So anyway, that's my marketing pitch for Google Colab. So let's get into it. So the first thing that we always want to do whenever we run Python code is import basically all of the libraries that we're going to be using. So you guys have probably seen a good decent number of these libraries before. Okay, no, screen share goes. Okay, well, Zoom is being weird, and we will disregard that for now. So anyway, going back to the imports, the first thing that we're going to do is import the standard things I like to import for basically any project that deals with large data sets are NumPy, which has a ton of mathematical commands. And then also you can import it as NP or as whatever you want. If you wanted to import a library that's called, I don't know, flying cars, but you want to refer to it as dogs or something, you could very easily do that. So importing it with the as command basically means you don't have to write out the whole name. You can write out an abbreviation, which is awesome. The next thing that we're going to do is import pandas, which we've used a little bit in the past in order to go between different file types like CSVs and SQL databases and pandas data frames, which is what we're going to be using today. So basically, pandas data frames are, they're sort of like big two-dimensional arrays, but it also combines those abilities with like an Excel sheet. So you can have like names of columns, rows, and all sorts of other stuff, which is very cool. The third thing that we're going to do is add in some plotting features because, hey, who doesn't like a nice looking graph? So for that, there's a really useful library called matplotlib, which I highly recommend you guys check out. You can make some really, really cool graphs using that. And then we've got a sub-function of that called pyplot, and we're going to import that as PLT. And then we also have Seaborn, which is another graphing mechanism or graphing library, and we're just going to import that as SNS. And then lastly, we're going to import the sklearn, which is so sklearn or scikit-learn is one of the multiple main machine learning libraries used in Python. So there are three big names to know about. There's sklearn, there's Keras, and then there's PyTorch. And then there's also TensorFlow. So these are like, if you hear these names being thrown around, just know that those are basically big machine learning libraries that have different benefits and downsides, like Keras, for example, and PyTorch are great at GPU acceleration. sklearn is good, fantastic for regression stuff, etc. So if you're interested in this stuff, I highly recommend checking those tools out. PyTorch and Keras have fantastic documentation and official tutorials as well. But we won't be doing that today. But if you guys have questions about those later, feel free to let me know. So the other good benefit about using a Jupyter notebook in this Google Colab is you don't have all of your code written in like one giant page. You can break it up into blocks like this, and you can run each block on its own. So instead of, say, running like 100 lines of code and then putting debug statements in like every 5 lines and then trying to figure out where you threw your error, just run a block. If the block checks out, run the next block. And if that block checks out, run the next block, and so on and so forth. So it really helps to break down problems and makes debugging infinitely simple. So if we run this one, all of our imports checked out, which is perfect. And then the next thing that we're going to do is set up our data sets. So here you'll notice that I've got a link to a GitHub right in here. Let me see, can I click on this? Yes, all right. And we're just going to use pandas read CSV function and put this stuff into a data frame that I'm calling train. So one thing that you'll notice here is at the end, so of this string for the URL, I've put raw equals true. So does anybody know or have any ideas as to why I might want to say that when I'm importing from GitHub?
Well, when you're looking at a repo in GitHub, you would access the raw just to get the actual text data for what you're trying to get. So you're not getting any of the fluff.
Exactly, yeah. So this is what the raw data file looks like here. So again, it just gives it to you in a very simple text format. Yeah, nothing super weird. Versus if we go to the main like GitHub link for this, it looks very nicely formatted. You've got all this other stuff with like the links, the whole HTML page, the beautiful looking table. But of course, if you try to import that, which we can actually try experiment with. Here, let me copy paste this, comment that out, remove the raw equals true, save that, and run it. You'll see that we get a parse error because it says it expected one field and saw 371. So you can't really import it straight from the GitHub link like this. There's two ways to import it from the raw data. The easiest way, in my opinion, is to just take the GitHub link and then put a question mark at the end of it and specify raw equals true. And if you do that, it'll automatically redirect to the raw link. The second one, as you guys can see up top here, is you can go to raw.githubusercontent.com and then put everything after the github.com in there. It's a little bit more complicated. Do whichever one you prefer, but I just find using the question mark raw equals true is the easiest approach. So let's rerun this. That checks out. So basically, if you get an error, then if you don't get any errors, you'll have a little check mark. And if you output something, it'll show up right underneath the block. If you do get an error, here, then you get a nice little red thing. It tells you what the error is. It has an automatic link to Search Stack Overflow, which is one of the best features ever. It can also show you exactly where the error showed up in the line, and these two both show up in red too. So And if you have browser notifications enabled, if you're like, say, running a long piece of code, it takes a couple minutes to run, you can go to another tab, work on something in the meantime, and then your browser notification will show up saying this completed successfully or it didn't. So basically, Google Colab is really good about error notifications. All right, so we've uploaded our data into the pandas data frame. And now let's get some information about our data set. So there's two separate functions that I'm running here. The first one is .info, and the second one is .head. So I think we may have used these functions before. Have you guys seen these two functions? And if so, do you remember what they're used for?
I know
Okay.
dot shows like the first, I don't know, top part of a data set or something.
That's correct. So .head shows you the first bit, and then .tail shows you the last bit. Usually it's like the first 10 rows is what I'm going to say. But you would want to check the documentation for that. But basically, and you can also specify how many rows you want it to show as well. Like you could say head 5, and then it'll only show the first 5, for example. But .info is also very useful, especially if you're dealing with a data set that you've never used before and you want to figure out what's in it. So let's hit the run button. And I'm also going to just pop open the CSV here. So again, just because this is a CSV file, there's a lot of stuff going on here. So, we've got all of these names, strings, numbers, lots and lots of random numbers and lots of rows. What does all of this mean? And for that's why we can use info to get a better idea. So first off, it tells us what type this is, and this is a pandas data frame. It gives us a range index, which is basically how many rows there are. And here it says there are 891 rows, going from 0 to 890. And then it says that there are 12 data columns, and they number the columns 0 to 11 because we always like to start out with the 0 index. And here we just have names for the columns. So passenger ID or ID is basically just going to be your account. You can think of it like an ID in a SQL database. Survived is going to be whether they survived or not. P class is going to be the class of the passenger. Name, sex, age are all pretty much the same thing. SIB SP is the number of siblings, believe that were on board. Yeah. And then Parch is the number of parents and children. Ticket is the ticket number, fare, passenger fare, cabin number, and embarked is the port of embarkation. So that's why they've got, for cabin, you've got things like Charlie or C85. For fare, you have a nice little decimal. For ticket, you have a lot of numbers and strings, and names are obviously going to be just a long string. So keeping the different types of data sets or data types in mind is very important too, which is exactly why we have this D type column. So it says, all right, for example, survived is either a 0 or a 1. So the data type is going to be an integer. Name is going to be a string, so that's going to be an object. Age is decimal, so it's going to be a float value, etc. One last thing to keep in mind is the number of null and non-null values. So a null value for our purposes here is basically a value that doesn't fit with the data type or just like a blank field. So for example, are there any here? Yes. So if we look in cabin and we look at passenger 0, so that will be Mr. Owen Harris Brond. So we see that he's got a ticket, he's got a fare, but he does not have a cabin. And NaN here just means not a number, which I think is kind of funny because all of the cabins are objects and strings, not numbers. But basically having a NaN or not a number value can throw a pretty big loop or error in your code. So for example, let's say that let's say that these were all numbers in the cabins. Now we wanted to add up all the numbers. So you'd go, all right, NaN, how do you add an NaN to, let's remove the C, and how do you add NaN to 85? You can't add, you can't do that. So Python will go and say, blah, error, we can't add these two things together. What do we do? So because of that, that's why rooting out null and not a number values is extremely important. And we're going to do that a little bit later for something called pre-processing, which is where we eliminate sorts of erroneous data things and make sure that our data is in a nice, appropriate format before we send it off to the machine learning stuff. So before I continue on, does anybody have any questions so far about the data set or what it shows or anything like that? Okay, I will keep moving on then. And also, if you guys are on the link that I sent in the Google or in the Slack channel, you guys should be able to see me run each of these cells as well and have the outputs show up on your own screen too. And also one really cool thing that you guys should be able to do is if you wanted to run this Google Colab on your own, just go to File, save a copy. I'd say just save a copy in Drive, and then you can run each of these cells along with me too, which I think is a really great feature. So if you guys want to do that, feel free to. All right, so the next thing that we're going to do is now that we've got information about the overall data set, what sorts of things are involved in it, what sorts of values we have, let's get some details about the data set. And for that, we can use the describe function. So this describe function is, in my opinion, pretty cool because it gives us like average values or more like statistically relevant values for our columns. So one thing to notice here, all of the columns listed are not object type. They're all either integer or float type. And that's because we can't really take a mean value, for example, or an average of all the names. There are ways to describe those columns as well, but those aren't really relevant for us right now, but you can always check those out. I believe those some of those should be linked in the links all the way at the top. And basically, this just gives us all the statistically relevant details. So for example, we see here that most of these have 891 counts, which is the number of rows that we have, but age is missing like 170 something values, which is a lot. So you're going to need to find a way to fill in those missing values in age. So we'll get to that a little bit later. The next thing that we can do is get the means and standard deviations and minima and maxima of each of these columns. You can see that for survived, it says just about 40% or 38% of all the people on board the Titanic survived. If we were to add up all the zeros, add up all the ones, then divide it by 891. This also shows us what the minimum and maximum values are. So the ages, for example, range from somebody like half a year old to 80 years old. Most people had about half of a sibling on board the Titanic, and the average fare that people paid was 32, I'm going to say probably pounds or dollars, but something like that. So this is just basically a bunch of useful information for us to know about to make sure that our results later are accurate, but also it just tells us cool stuff about the data set that it may be useful later on. So the next thing that we're going to do is go back to what I was talking about earlier, checking for null cells. So let me hit the run button here. So the way that we check if cells are null or not is by using this isNull command in our data frame. And what the total does here, so the first line here says, all right, let me go through the whole data frame, check all the cells that are null, sum up all the cells, and then sort the values in descending order. So then the rest of it is just getting some percentages and rounding them and basically just making it into a more user-friendly format. And at the end, we can go down here to see how many null and non-null cells we have. So for example, the cabin seems to have a lot of null values. Remember, we only have about 900 rows, and Cabin has over 2/3 of those rows are null values, or over 3/4, I should say, which is a lot. Then we've got age. We have 177 null values, which is a decent amount. It's, it's not too bad, but it's still a lot. And then we've got like 2 for the embarked, and we've got none for the others. So this is really helpful to give you an idea of, for example, if we were to create, it's to process our data right now and send it through a machine learning algorithm, do we really need all of the information in the cabin column, given that so much of it is null and for our purposes basically unusable? Or do we still really have to include it? For example, if that was, let's say, a very vital class and we still had to include values from cabin because our whole project was focused on correlating, say, the cabin number of people in which cabin with their survivability, then we might need to find another data set or something better. But in this case, we don't really have any particular goals of that nature, so we don't really need to bother about the null values that much. And we could probably just drop that column and not use it if we needed to. So here is also a way that we can fill in the null values. So let me just run that, and that worked perfect. So the first thing that we're going to do is we can print out the total null values, which is just using the is null, and then you sum the values just like we did up here. And the second thing that we can do is use this really cool function called fill NA, which basically, if you go through a given column, it will fill all of the values in that column with whatever you tell it to. So, for example, if we go through the age column here, remember age, we had like 177 null values. For the people who we don't know how old they are, we will just fill them in with the mean age, for example, right now. And then for cabin, for example, we just fill those in with an N, and embark, we can do the same thing, just in order for it to say N, like we don't know. And if we do this and we go down to the bottom, it says, so initially we had 866 null values. And remember, we had 891 rows. So this is, averaging it out, you could say that it's almost like having 1 null value per row. But using the fill NA method, we can get it down to 0, which is very helpful. So whenever you have a null value, you always want to think about, do I need the data that this null value comes with, or should I remove it, or is there something I can replace it with? And depending on that, you can either use, there's also a function called drop NA, which drops the null values. There's fill NA, and there are more functions like this that we can use. So just make sure to keep those in mind. Okay, so my little tangent about null values over. Let's move on to analyzing the data. And this part is one of my favorites because it gives you all sorts of cool pictures. We're only going to go over 2 or 3 right now because the main focus of today is going to be on the different types of algorithms and regressions that we can do on it. So let's start with the main one. Let's look at gender versus survived. So it looks like basically about only 0.2% of the people who survived were male, while about 0.7 or 0.8 were female. Which is pretty interesting. The other thing that we can look at is passenger class versus how they survived. And we've got 3 classes on board, first, second, and third. And take a look, the higher class you are on the ship, the greater a chance of survivability. It's a lot more obvious for, say, comparing class 1 and class 3, but class 2 ranks up there as well. So also, the other thing to note here is that I'm using the SNS bar plot. And again, please go ahead and take a look at that, remembering that SNS stands for Seaborn. So if you guys are interested in using these sorts of bar plots in your own code, please take a look at the library. Again, it's really helpful. So here, for an example of a more complicated plot, we can use this one. So we've got passenger class on the bottom, we've got survived on the top. We can color the data using gender, and then the data that we're getting all of this from is going to be our DF train. So the so remember, the X and Y axes and that it's getting are going to be the column headers from our data frame. So keeping that in mind here is pretty important. So the last thing that we can look at is looking at the age of people relative to their survivability as well. So if we look down here, we can compare, say, babies versus students versus the elderly, and correlate that with their gender as well. So for example, the survivability of babies seems to be pretty high overall compared to, say, teenagers or adults, which is pretty interesting. But again, there's probably a smaller number of babies on board than teenagers or students, and we can get those numbers if needed as well. But the main reason I included this graph here is because this uses basically what we'd call categorization or binning. So for example, here you'd have 891 data points, each of whom would probably have a different age, or maybe we'll have a couple of shared ages, but you'd have, like, for example, 1 and then 25 and then 94 and then 36 and 42, etc. And if we were to plot like a dot plot or a graph of each of those people with their age versus their survivability, or whether they survived or not, we would basically get something that told us absolutely nothing about how age correlates with whether they survived or not. Because you'd have one person survived, and then they're like another person a year older didn't, and then 2 years older they did and didn't and did, and you can see why it would get really messy. So this is why categories are extremely important. So using this function called getCategory, which is again from one of the tutorials I sent above, it basically just uses a bunch of if state and elif statements in order to put people's ages down in these different categories so that we can analyze how the categories differ from each other. Another thing to note is for when you have really big sample sizes like this, using categories is helpful not just to compare across categories, but also in order to, again, if we have, like, let's say 1 million people, running a machine learning algorithm over 1 million people is going to take a while. But if we were able to break it down to, for example, first we're going to run the algorithm on all the babies, and then on all the children, and then on all the teenagers and all the students, etc. It makes our runtime a lot more efficient from the standpoint of just binning the data into these categories. So another really good thing to keep in mind when you're doing machine learning is keeping in mind, your sample size, which in this case is relatively small, and thinking about do I need to break this down further in order to make the machine learning go a little bit faster, or can I just do it on the whole set? And that's all the graphs so far. So before I move on to what I think is one of the most fun sections, pre-processing, does anybody have any questions? Okay, again, if anybody does have any questions, feel free to pop it in the chat, talk on mic, raise your hand if you'd like to. And with that, let's move on to pre-processing. So if we go back up to the info tab here, we can see that, again, remember most of our data is integers and floats, but we do have a couple of data things that are not. We've got, for example, name is obviously going to be a string. We've got something like ticket, which is obviously going to be a string as well. You've got fair, which is a float. You've got survive, which is an integer. I've just got all of these different types, and it's a little bit difficult for a computer to try and find patterns, because remember, machine learning is all about finding patterns, especially the type that we're doing, which is regression. But since it's trying to find a pattern, it's a bit difficult to find a pattern between strings, for example. So what we need to do is we need to turn everything into a number somehow, anyhow. And sklearn very nicely provides us a feature to do that called pre-processing. So it's a library here called pre-processing that we can import. We'll look at our main features of, like, say, cabin, sex, and embarked. And then we're just going to turn those features, because remember, these features originally were strings, and machine learning doesn't do great with strings, so we need to turn those into numbers. And this does that for us. It's not too complicated of a function, thankfully. You just run preprocessing.label encoder, and then you just want to fit, quote unquote, the data in each of those feature columns to that encoder. And then you just need to transform the data. So it's a little bit complicated, but thankfully it's a whole lot less complicated than making your own preprocessing function. And let's hit enter, run that, and let's go back and look at our header here real quick. So here, we've got name as a big string, sex either male or female. We've got cabin is NAN or C85, and embarked is either S or C. But if we go down here and take a look at the new improved Titanic data frames data set, we've got survived as 0 or 1, class 1 or 3, and we didn't encode name, but we've changed the sex one from this 1 to from male and female to 1 and 0 respectively. Same way, we didn't change ticket, but if we take a look at cabin, we've changed it to a number. And I assume there were probably more than 146 cabins that we know about. So because of that, they've got numbers assigned to each of these. And then the embarked is going to be whichever port they embarked at, and that's going to be a number as well. So basically encoding turns a string or some other yucky data type and turns it into a number, which is great. So the next thing that we're going to do is, again, we want to pre-process our data, and that means make it look nice. So because of that, we've got, again, all of our functions from before about, filling in all the null values in the data frames that we want. For us, for the purpose of machine learning, getting the name or the passenger ID or the ticket number that they had isn't really very important. So we can just drop those tables or drop those columns. We can format the features a little bit, which is, again, exactly what we did up here with the pre-processing. Some people call it formatting, some people call it encoding, some people call it pre-processing. It's all the same thing. And then we've just got our overall function down here called transform features. So just run this, make sure that the Collab knows that these functions are going to be run. And then we're just going to reload the data set one more time because we're going to redo the pre-processing on it. And now we can also pull out our predictive data sets. So again, let's go back to the CSV file for a second here. Okay, so let's take a look again back at our headers. So the main thing that we really care about is figuring out who survived, right? So the survived column is really important to us. But how can we create a model to predict, for example, if someone could survive or not, or to tell us who survived or not? We need to make that based off of something. So we're gonna make survive based off of all this other stuff. So if you guys remember, like, for example, your simple XY or XYZ plots back from middle or high school math, we're basically doing the exact same thing here. So we've got our X and Y axes, so to speak. So our Y axis, which is like the thing that we want the result of, which is, if somebody survived or not. Our Y axis is going to be that survived column. It's going to be, did they survive or did they not survive? And then we're going to base all of that Y data on all of the other columns. So we've got, we're going to first drop the survived column because that's it, or that's going to be our y-axis, and we can't have the y-axis be involved in the x-axis. And then we're also just going to transform the features and pre-process the data using the functions that we wrote up here. So if I run, it does that. And then there's one last thing that is really important for us to do whenever we're running machine learning code. The first thing is to charge your computer because you don't want your computer dying in the middle of a run. The second thing that you should do is split your data up into training, testing, and validation data sets. So the three data sets you can have one really big data set and split it up into these three categories. You can have 3 data sets that you use to split into these categories too. But generally, what you want to do is have the main part of your data be used for training, which is, again, it's going to pour over that data. It's going to read through it. It's going to use that to create its model. Then we've got testing, which, okay, after it's created the model, then let's use a smaller portion of the data, a small subsection of it, to test on the data and just make sure, hey, is this doing what I expect or is it not? And how well is it doing what I want it to do? And the last thing that we want to do is use validation data, which basically helps it train better. Because while it's training the model will also test on that validation data at the same time. So it's sort of like, you can think of training like if you're reading a textbook, and like, yeah, basically training is like reading a textbook. Testing is like doing the problems at the back of the chapter. And then validation is like working on examples in the textbook while you're reading the textbook and being like, oh, okay, I made a mistake here, so I'm going to go back and fix that next time around. So if that example helps, that's great. If it doesn't, there are probably better examples on Google that you could use. But basically, if we have only one data set, like we do in this case with the training data, we want to split it into training, testing, and validation most of the time, but we'll do that part a little bit later. So we can use this train test split function from sklearn, which I imported way over at the top. You can take the test size. So for this basically means that we're going to have 80% of the data be training, 20% for testing, and then random state just says how random do we want to make our selections. So we'll run this. And also you can see how quickly the code runs here because we're using a relatively small sample size. If this was a larger data set with, say, like hundreds of thousands or millions of data points, it might take a little bit longer to run the data pre-processing stuff. But yeah, so that's all I've got about pre-processing. Before we jump into the really fun part, which is the machine learning bit, does anybody have any questions about data set pre-processing, the data that we're using, or anything else? Okay, I'm going to assume not. So keep moving forward then. So for the machine learning time, we're going to be using the sklearn library, which you guys played with a little bit last weekend as well. And there are a bunch of different models that we're going to be looking at. So the first three things that we'll be using are different classifiers. So again, going back to what you guys did last weekend with chat, classifiers will basically tell you, given a bunch of data, is something, what group is something in, right? So an easy way to think about classifiers, for example, is if you have a picture, your brain tells you that's a picture of a car or a picture of a dog or a picture of a blade of grass or something like that. So that's basically what a classifier does. And we have a couple of different classifiers that we'll be playing with today, just in order to compare and contrast the models. We've got decision trees, random forest, and logistic regression, which basically just tries to find a curve that best models the data. And the last import here is going to be a metric called accuracy score, which basically just tells us, in a very broad sense, hey, how good am I approximating this data? Because one thing to keep in mind is that different machine learning algorithms and different classifiers will give you different levels of accuracy, depending on the type of data and the data set used. So it's always important whenever you start doing machine learning based tasks to try out multiple classifiers or multiple algorithm types and just see which one fits best. So, and something similar like we'll see in a little bit is if you're designing your own neural network from scratch, it's also very important to just play with the features of the algorithm, check the number of nodes, number of layers, change those up a little bit and see where you reach the best happy medium, where it doesn't take too long to train, but it's got very good accuracy. So let's run all these import statements down. And then down here, we're going to be creating our classifier models. So here we've got our three classes. We've got our decision tree, we've got our random forest, and we've got our logistic regression. And again, these first two are initialized with random state because that just tells us, hey, how much randomness do I want in the way that I'm going to be training? And the way that we train these models with sklearn is actually super easy. So it's literally 3 lines. That's it. So going to, for example, a decision tree, we just say the class name dot fit, which is basically, again, we're fitting the model to the data. So that, again, if you think about it, like you have a bunch of data points, you take like a piece of string and you put the string through the data points. That's a nice way of visualizing how this works and what fitting sort of looks like. And then we want to put our two axes. So in the X axis, we're going to say all the stuff that we want to use in our prediction. And the Y axis is going to be the thing that we want to predict. And then down here, remember that we only want to train or fit on the training data, but we want to predict based on the testing data. So what we'll do is we're going to compare the predictions, which is DT pred here for the decision tree, to the testing true values for who survived or who didn't. And then we'll get the accuracy score down here that compares them. And we basically just replicate that for each of these models. So again, the main steps here, I'll write these out here. So we're going to create a class, and we're going to the model to the data, then to the training data, predictions for testing data, and predictions to actual. So those are really the four main steps that you'll use whenever you're creating a machine learning algorithm. You want to create your model, fit the model, get the predictions, and compare the predictions. So if we run this really quickly, let's see how each of these stacks up. So disregarding all of the warnings, because thankfully these aren't errors. If it was an error, we would have a big red flag. Let's take a look at these three metrics right here. So the decision tree accuracy is decent. I mean, it's a bit lower than 80%, but it's lower than random forest and logistic regression. So these are decimals, but you can turn these into percents pretty easily by just multiplying by 100 and putting a percentage sign, which is generally how people prefer to see the data. It's easier, if you're presenting this, for example, to say something like, we were successfully able to predict over 85% of survivors versus 0.85 of the testing data. But these just map over to a percentage. And it makes it's nice to have a way that you can easily compare how good or bad our different models are. So now that we have our models and we've got our predictions, and again, let's say if you wanted to also get a prediction of whether somebody survived or not, you would just use this, again, the dot predict function, and you just put in your input values, and then the result would just be, did they survive or did they not? So it makes it's not too difficult to use either, which I think is fantastic. The last thing that we're going to do before we move on to fine tuning the model is validate the data sets. So again, this goes back to what we were talking about earlier about training, testing, and validation. But we're not, here we didn't split it up with a validation set and some other things like, if you did this with Keras or PyTorch, they do highly encourage you to do that. But what we're going to do for sklearn is just use this little handy function called cross-val score or cross-validation score. And this will basically tell us during each run, how did it do? What was the mean percentage for accuracy? And what was the standard deviation for overall accuracy? So if we run this and we go down here, so this is, again, we're training it in each batch or each epoch, so to speak, or I believe each is 10. We can see that the score scouts are pretty low, only about 73.6%. It goes up to 83, and then it peaks out around 87.3, and then it goes down a little bit, and then back up, and then it starts plunging downward again. So this tells us that the model may be overtrained, which means that basically if you feed the model so much, like too much data to train on, it's eventually just going to say, okay, I think I got it, and then proceed to do a whole lot worse going forward. So sometimes overlearning is a bad thing in the context of machine learning. And then down here, we've got our mean. So it did pretty well, about 78%, with a standard deviation of about 6%. So basically the cross-validation scores are a helpful indicator to tell you, A, while it's training, how good or how bad is it doing, and B, in some other places, again, like Keras or PyTorch, and I believe in sklearn too, you can actually write some code that lets the machine learning algorithm do the validation while it's training, but at the same time, look at the validation scores that it gets while training and say, okay, hey, I did really bad on that last batch, so I'm going to try to improve on the next one, instead of just saying on to the next batch, on to the next batch, on to the next batch. So that sort of helps you fine tune your results a little bit, get some better results as well. So really quickly, I want to show you guys one or two graphs, and then I'll take some questions. The first thing that we're going to take a look at is looking at precision and recall. So precision is basically, for us, it would be how good is it at predicting survival for a given passenger, right? So like if I give you a passenger with a name, an age, a class, how accurately will it predict that person survived or not? And then recall is going to be sort of like flipping it on its head. So it's like, how good is it at predicting survival for the overall data set? So if we hit run here, we see that if I give the algorithm a passenger, 74.4% of the time, it'll tell you the correct answer for whether this person survived or not. But for recall, it does very, very marginally worse at 73.3% of correct predictions for the model overall, but they're fairly similar, which is great. So what we want to make sure is that precision and recall are generally high and ideally generally close as well. And we can also plot a very cool graph of both of these as well. So for example, we can see that the precision goes up over time, which is exactly what we want. But after a point, sometimes it may go down. And then recall starts out pretty high over time and then goes down, which again, it's not the biggest deal in the world, but it is still something important to keep in mind. So precision and recall are, in addition to your accuracy scores from above, precision and recall can also be very good tools in order to help you figure out how to best fine tune your model. And there's one more thing. Let me see if I can find it. Perfect. Okay, so there's one more thing that we can do, which is while we're training, we can, again, use the validation code or use validation and our validation data set in order to get a better idea of how good our model is while it's training. So what we can do is while we're getting our validation, we can get something called our validation mean average error, which basically tells us how different our predictions are from what we expect. Again, this is all during training using that validation data set. And here's a graph from a tutorial from Keras about predicting house prices. And epochs are basically the number of times that you train and the number of data points that you use. So initially, the mean average error is really high, which is what we'd expect, because you have the model has no idea what it's doing. It's just started training, and it's just a little bit all over the place. Then, as we continue training, the mean average error goes down, which is great. You always want, if the mean average error kept going down, that would be even better. But then it starts going back up again, which is kind of weird, because you'd expect that as you read more, for example, about a certain subject, that you'd get better at the subject and understanding it. But again, if you read too much about a subject, your brain might, for example, start to zone out and not really understand everything that's going on. And that's sort of like what's happening here. So as we increase the epochs even more from, say, like 100 to 200 to 3 to 4 to 5, the mean average error goes up again, which means that the model is doing worse with more time. So graphs of these sorts of epochs versus validation mean average error can give us a good indication of where to stop learning. wherever we get the lowest error. And here, for example, that would be right around like 80 to 100 epochs roughly. And if we do that, we'd get a lower loss and a lower mean average error. Okay, let me see, do I have anything else in here? Not really. Okay, but yeah, so that is a very brief overview of machine learning and how it works and what it can be used for. Does anybody have any questions, either about the stuff that we talked about in the code or any other general machine learning topics?